to get things started, I just want to take a quick look in Canvas. To look at what's in there right now.
Mr. Mosley.
What's up, Valentine?
I was gonna go right now, then I just got a call from David Monkey. I don't know what the freak. I got a call from David Monkey.
It should have said David Mosley, but you know.
I thought I saw wrong. Never mind. I thought it was Monkey. It said, who's calling me? Who's calling me by David Monkey?
Yeah, I don't know. I don't know, man.
All
right. Cool. So, excellent. Thank you all for being here. We're going to take a quick look at Canvas. A few things here. Obviously, the calendar is being populated with lots and lots of things. Here's class for today, the 27th. Right here, we already have a link to the presentation for today. I'm almost done with the period 3 recording. We'll get you guys recording in here before the end of the day. This is the only day that I will see you guys this week. I won't see you again until Tuesday next week. So that's kind of a bummer. So there's that. If we take a look at our modules, right, in our things you might need module, right, this one is just kind of like a catch-all for things that I think we should have access to. We've got our formula sheet and tables, and then I have this new page here, how to use table A. This actually has a couple of videos that I made last semester showing scenarios and problems on how to use table A in different contexts. So remember, we're continually kind of going back into table A using normal approximations and normal distributions. Even in this chapter, it's going to keep coming back up. It's not going anywhere. So I've got some review on that available. And if those don't give you what you need, please let me know. I'll make something else. In our chapter 6 module, I'll get the solutions for the Desmos activity from last week in here shortly. Section 6.3, there's going to be another Desmos activity in there that will be essentially just a extra activity. It will not be assigned. It's not going to be worth participation because we don't have time to do it this week. And unfortunately, I can't push it till next week because we have to start chapter 7 next week. So there's that, but there will be an activity that will be available if you'd like to see some other problems, practice problems. Otherwise, I do heavily suggest doing or taking a look at and trying the practice problems for section 6.3 after today's lesson. In our chapter 6 assessments, right, the multiple choice and free response question / self-assessment, those are all available and ready for you. Above that here, I've added the chapter 6 worked review FRQs or free response questions. This was my big project yesterday. It took me a few hours to get done. And this is basically a 40-minute video showing examples that require you to use the knowledge from chapter 6 on random variables, finding probabilities with random variables, combining and transforming random variables, and then the unit today or the section today on binomial and geometric random variables. There's parts of these problems in all of these. In the 5 problems I work through here, that should help prepare you for the types of problems on the free response question in the assessment for chapter 6. So there is that. All right. And then finally, remember, if you're trying to move at your own pace, chapter 7 will be opened up next week when we start chapter 7 as class. If you want to try and get a peek into there, you need to complete the 2 assessments first, where there's a multiple choice and the free response / self-assessment. And can you guys remind me, did I review with you what my expectation is, how to do the chapter 6 FRQ / self-assessment? Did I go over that already? Maybe. I don't remember, guys. Okay, well, we'll quickly go over it because I'm not getting any confirmation that I did. So this is what it looks like. It is an assignment. It is not a quiz. This is just to allow you more flexibility on how to submit this. All the problem details and what you should do is in the details of the assignment. Right? There's two sections. For response question is section 1. Self-assessment and reflection is section 2. There are 2 problems in our free response question area. There's one about random variables, probability distributions, and combining random variables, and another on binomial and geometric distributions. All right, so you must complete both of these problems. I highly suggest that you use a submission type that allows you to show your work and show your thinking so that if things are incorrect, I can give you valuable feedback based on the work that you've done. All right. Then we have our self-assessment and reflection. There's the pick your grade part. There's a little sentence starter here for you, and a reflection question. Your submission for this assignment should contain all of your work for both sections of the self-assessment, right? The free response questions and the self-assessment reflection. Right? You can choose to do this as a text entry, right? In which case you get your little text entry box. You can type up your responses to the questions. You can also choose to do your work on paper and then upload the image of your work if you want to do it that way. You have all those options available to you in the text entry. All right. You can also choose to do a URL, right? If you want to share give me the URL of a Google document as a shared document, you could put that in here if you like. If you want to make a Google site that has your solutions, cool, more power to you. You can choose to upload a media, right? You could record yourself answering the questions. That's a possibility. You can upload a file, right? If you're uploading a file, right, remember what we saw last year when we do a file upload, you need to have this be a single file, right? So if you've done your work on paper and you've taken pictures of it, you need to make sure all those pictures are contained in a single file to upload that one file. Otherwise, I'm only going to get one picture of one page of your work, right? So what I would recommend is if you're going to do it that way, right, do your work on paper, take pictures of it, and submit that as like a PDF. Use a document scanning app on your phone, right, if you're going to do it that way. There's lots of them out there. Lots of them are free. They'll allow you to take multiple pictures and have those all be a single file. So there's that. So you have lots of options. Right? If you're going to upload a file, you can have a file uploaded. Right? Where's my stuff? Let's see. I have lots of files. Here we go. I wonder if it'll let me do more than one. Let's see. Nope. Oh, maybe. Hey, there we go. We can do more than one. Hey, found out something new today. So there you go. Lots of files to upload. And there's some examples. All right, is there anything I can clarify about the expectation for the self-assessment and free response questions? Stupendous. All right, so then we're going to start our lesson for today. Now's the time that if you have a notebook or you're writing your notes on pieces of paper or you're taking notes in some way, shape, or form, get that ready. We're going to have some notes today. Be prepared. All right, so here we go. And as always, if you have questions, you want something explained further, you need me to pause or go back a slide because you didn't finish writing something down, please raise your hand, let me know, unmute your mic, shout at me, or just type in the chat. I'll be watching stuff. All right, so with that, we'll start. We're in section 6.3 today on binomial and geometric random variables. All right, we'll get some new formulas today. We'll get some new conditions that we need to consider. It should be fun. So here's our goals for today. All right, after this lesson, you should be able to determine whether the conditions for using a binomial or random variable are met. All right, compute and interpret probabilities involving binomial distributions, calculate the mean and standard deviation of a binomial random variable, interpret these values in context, find probabilities involving geometric random variables, and when appropriate, use the normal approximation to the binomial distribution to calculate probabilities. This is not going to be, this last one won't be emphasized because as you see here, it's not required necessarily for the AP Stats exam, although as an overarching statement, anything in the textbook is fair game. All right, so that's what we'll work on today. First, binomial settings. All right. When the same chance process is repeated several times, we are often interested in whether a particular outcome does or does not happen on each repetition. Some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. They are called binomial random variables. A binomial setting arises when we perform several independent trials, that's important, of the same chance process and record the number of times that a particular outcome occurs. We can think of that as a success. The 4 conditions for a binomial setting are as follows. Is it binary? Right? The possible outcomes of each trial can be classified as a success or a failure, right? You can either get what you want or not get what you want, right? Binary, 2 options. Independent. Right? Are the trials independent? Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of any other trial. This is the same definition of independent that we've seen previously. In order to be a binomial setting and have a binomial random variable and have binomial distribution, these trials must be independent. Too fast. Number. The number of trials n in the chance process must be fixed in advance, meaning you have to know how many trials you're going to do before you start. All right. So maybe we're running a experiment, and in this experiment, we're going to have 50 trials of some chance process. Right? And each time we run this chance process, we record how many times we have a certain outcome. All right, and knowing how many trials we're going to do ahead of time, right? That's the number. It's not like I've been doing this experiment for a few days and I'm like, okay, well, I think this is enough, so I'm going to stop here, right? That doesn't fit this condition. I didn't have that fixed before I started. Success. Right? There is the same probability P of success on each trial. Right? This ties into independence. Right? If events are independent, that means the probability of success is the same from trial to trial because knowing what happened didn't change the likelihood of the thing happening again. Right? So these are the conditions: binary, independent, number, and success. Lovingly referred to as bins. All right, so to check to see if something is in a binomial setting, we have to check our bins. It's a nice little way to remember what to look for. All right, so now we get binomial or random variables. Consider tossing a coin n times. Each toss gives either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome on any other toss. If we define heads as a success, then P is the probability of a head and is 0.5 on any toss. The number of heads in n tosses is a binomial random variable x. Probability distribution of x is called a binomial distribution. The count x of successes in a binomial setting is a binomial or random variable. The probability distribution of X is a binomial distribution with parameters n and p, where n is the number of trials of the chance process and p is the probability of a success on any one trial. The possible values of X are the whole numbers from 0 to n. So that leads us to binomial probabilities. In a binomial setting, we can define a random variable, call it X, as the number of successes in n independent trials. We are interested in finding the probability distribution of X. So here's our scenario. Each child of a particular pair of parents has probability 0.25 of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable with n equals 5 trials and probability p equals 0.25 of a success on each trial. In this setting, a child with type O blood is a success, S, and a child with another blood type is a failure, F. What's the probability of X equaling 2? What's the probability of having exactly 2 children with type O blood out of the 5 possible children? It's also important to keep in mind here that we use the term success and failure without any indication of good or bad, right? It's just one of the things that we're tracking. The other stuff is what we're not caring about as much. We're not tracking those values necessarily, right? So here we go. One possible outcome would be to have the first 2 children have type O blood. So 2 successes in a row to start it off, and then the other 3 children after that are all not type O. Right, so the probability of this scenario happening is 0.25 times 0.25 times 0.75, 0.75, 0.75. We get 0.25 squared times 0.75 cubed, and we get 0.02637. All right. So there's about a 2.6% chance of the first 2 children being type O. All right. However, there are a number of different arrangements in which 2 out of the 5 children have type O blood. That's not the only way for this thing to be satisfied. Right? We have 10 possible combinations. The first one we already calculated. Right? In each of the arrangements, right? So first arrangement, we have this probability. The second arrangement results in the same calculation. Third, fourth, fifth, all 10 of these give me the same exact 0.02637 probability. All right? And that's because ultimately we have 0.25 multiplied by itself 2 times, 0.75 multiplied by itself 3 times. No matter how we arrange it, that's what we end up with. So therefore, the probability of X equaling 2, or of 2 children out of the 5 having type O blood, is 10 times the probability of one of these scenarios happening, which we end up with 0.2637. Note that in this previous example, any one arrangement of 2 S's and 3 F's had the same probability. This is true because no matter what arrangement, we'd multiply together 0.25 twice and 0.75 3 times, as I said previously. We can generalize this for any setting in which we are interested in K successes in N trials. That is, the probability of X equaling K is equal to the probability of exactly K successes in N trials, which is equal to the number of arrangements, right? The number of ways I can have K successes in N trials, times probability of success times K, or not times, to the power of K successes, times the probability of failure, 1 minus P, to the power of number of failures. Okay. In general, we do have this binomial coefficient, which helps fill this number of arrangements. The number of ways of arranging k-successes among n observations is given by the binomial coefficient. So that's what this thing is here. It's the binomial coefficient. And we read this as n choose k. In this tall parentheses, there is no division bar here. It's just an n on top of a k. And this is equal to n factorial divided by k factorial times n minus k factorial. For k equals 0, 1, 2, through n, right? Where n factorial is defined as n times n minus 1 times n minus 2 times n minus 3 and so on until we get 3, 2, 1. And it's also given and defined that 0 factorial is equal to 1, not 0. There's reasons for that. There's proofs of this. We do not have time for this in this class and is beyond the scope of our class. So, for example, right, 5 factorial, right? And when you say factorial, you should say factorial. It's very exciting. It's an exclamation part, right? 5 factorial is 5 times 4 times 3 times 2 times 1. Right? 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Basically, whatever number is next to the exclamation mark is multiplied by every number smaller than it till you get to 1. Right? That's what this thing says to do. Right? You can also do this calculation on your calculator. And to do that, oops. So if I want to do 5 choose 2, which is what we did in this previous example with the children and the typo blood, we'll say 5. And then you'll click on the math button. Math. Click over to highlight PRB, or probability. And we'll go to NCR, N choose R, which is the third option. Hit enter. I'm going to do 5 choose 2. Enter. I have 10 possible combinations. If we wanted to maybe do 6 choose 2, right? How many different ways can I have 2 successes in 6 trials? Right, we have 15. Right? This way you don't have to do this calculation and the factorial and all that fun stuff. Just plug it in your calculator, it will do the work for you. So now that we have our binomial coefficient, right, the binomial coefficient counts the number of different ways in which k successes can be arranged among n trials. Binomial probability, p of x equaling k, is this count multiplied by the probability of any one specific arrangement of the k successes. Right, and that's what we saw in our example. If x has the binomial distribution with n trials and probability p of success on each trial, the possible values of x are 0, 1, 2, through n. If k is any one of these values, the probability of x equaling k is equal to n choose k times the probability of success times k, or to the power of k successes, times the probability of failure, 1 minus p, to the power of number of failures, n minus k. So again, n choose k represents the number of arrangements of k successes in n trials. This calculation represents the probability of k successes happening. And we multiply by the probability of n minus k failures, or the amount of failures. So now we have a 3-step process on how to find binomial probabilities. Step 1, state the distribution and the values of interest. Specify a binomial distribution with the number of trials n, success probability p, and the values of the variable clearly defined. Right. Essentially, this is saying before you start doing your calculations, you should identify these things, and it's probably smart just to write them down. Be like n equals this, p equals this. My random variable can have values from here to here. Right? Have things be clearly set up and defined. Step 2, perform calculations. Please show your work. And you can do your calculations by doing one of the following. Use the binomial probability formula to find the desired probability from the previous screen, or use your calculator and use the binom PDF or binom CDF command and label each of the inputs. I will show you where to do these on your calculator and what they mean by labeling momentarily. Step 3, answer the question. Make sure you're answering the question that was asked, not just providing the result of the probability. All right. So now we have a couple of things that go along with each of these commands in your calculator. The binom PDF command will calculate probability of a random variable being equal to a certain number of successes. The binom CDF calculation is to determine the probability of a random variable being less than or equal to a certain number of outcomes. Right, so in the previous example, we saw the probability of X equaling K. Right, the probability of having exactly 2 kids with type O blood. Binom CDF would be something you would use if it's like, okay, well, what I want to know, what's the probability of having at most 2 children with type O blood, so 2, 1, or 0 kids with type O blood, right? Or we can use the complement rule to find out what's the probability of having 2 or more kids with type O blood, right? So 1 minus probability of less than 2, and all that. But these are the 2 specific calculations that your calculator can do. And when it says label each of the inputs, these calculations in your calculator require 3 inputs, right? You need to label the number of trials, right? The probability of success, and what's the value of K that you're interested in? All right. So if you're using one of these, so for example, suppose we're using this in our calculator to find the probability of having exactly 2 kids with type O blood, right? We would say, okay, well, I'm going to find this probability of X equals 2, right? And that is going to be equal to the binom PDF with N equal to 5, P equals 0.25, and K equals 2. This is what needs to be labeled for each of the inputs. This is clearly saying that I'm doing a binomial distribution and calculating the probability using a binomial distribution with N of 5, P of 0.25, and 2 successes. All right, so now that we know what this statement means, this is where we do it in our calculator. Okay, so we got our, let's make this a little bigger. Bam. All right, so in your calculator, you'll have to press second and then vars, which above it says distributions. Hit that. To get to what we want faster, we're going to click up to go to the end of the list, and we'll see option A and option B is binom PDF and binom CDF. If we go up to option A here and click enter, it's going to ask for those same 3 numbers we just identified below in the slide, right? We have number of trials, all right, that's 5. Probability of success, 0.25. X value, which in our labeling is K, right? The value of K, 2. I'm curious about what's the probability of having 2 successes. All right. We'll hit paste. It'll plug that into my calculator. And notice these are in the same order that we listed them over here. And we get the same probability as we had earlier in the example, 0.263671, and a nice big decimal for us, right? But about 26% chance. So that's how we can have the calculator do the work for us. But if you're doing that, you must show that that's what you're doing by clearly labeling the inputs properly, right? All right, so we got a couple of examples on how to find binomial probabilities. First, same context. Each child of a particular pair of parents has a probability 0.25 of having blood type O. Suppose parents have 5 children. Right, so we have our set number of trials, our probability of success, all ready to go. Find the probability that exactly 3 of the children have type O blood. Again, we're going to clearly define the things that we're going to be using. We're going to have X equal the number of children with type O blood. We know X has a binomial distribution with N equals 5 and P equals 0.25. So we will use the binomial probability formula for X equaling 3. So the probability of X equaling 3 is 5 choose 3 times 0.25 to the third power times 0.75 to the second power. And we ultimately get 0.08789. So about nearly a 9% chance of having 3 children with blood type O. Second question, should the parents be surprised if more than 3 of their children have blood type O? To answer this, we should calculate the probability of X being greater than 3. All right. Oh, pardon me. Excuse me. All right. So to do this, right, the probability of X being greater than 3 is equal to the probability of X equaling 4 plus the probability of X equaling 5. Right? We only have 2 other possibilities above 3, 4, and 5. So we do the binomial probability formula for both of these, X equaling 4 and X equaling 5. Notice we have to a 0 power over here. Remember, anything to the 0 power is 1, not 0. All right. So 0.75 to the 0 power is 1. All right, we get the final result of 0.01563, or about 1.5%. So the probability of having more than 3 children that have type O out of 5 is about 1.5%, pretty darn low. Right, since there is only a 1.5% chance that more than 3 children out of 5 would have blood type O, the parents should be surprised, right? The odds are not in their favor on that one, but doesn't mean it can't happen. It doesn't have probability 0. All right, we can also calculate the mean and standard deviation of a binomial distribution. All right, we can describe the probability distribution of a binomial random variable just like any other distribution by looking at the shape, center, and spread. We consider the probability distribution of X equaling the number of children with type O blood in a family with 5 children. We get the histogram and table here describing that distribution. Right, the shape, this probability distribution of X is skewed to the right. It is more likely to have 0, 1, or 2 children with type O blood than a larger value. The median number of children with type O blood is 1. Right. That's where we hit the 50th percentile based on our formula for the mean. Right, which again, the mean of X is the expected value of X, which is each outcome multiplied by the probability of that outcome, added up. We get 1.25. The spread, right, the variance of X is the sum of each outcome minus the mean squared times probability of that outcome. We're going to add all those bad boys up, and we get 0.9375. And then the standard deviation of X is the square root of the variance, which is 0.968. All right, and before you go through the trouble of writing down all these calculations, there's a shortcut, right? If I know I'm dealing with a binomial distribution, and I have the number of trials, probability of success, That's all I need to calculate the mean and standard deviation. I can bypass these long calculations. All right. But before I show that, does anyone need a moment to write anything down from this slide? All right. So here's our shortcut. All right. The mean and standard deviation of a binomial or random variable if account X has the binomial distribution with number of trials N and probability of success P. The mean and standard deviation of X are, right? The mean of X is N times P. And the standard deviation is the square root of N times P times 1 minus P. All right, so essentially the mean is the number of trials times probability of success. And the standard deviation is the square root of the number of trials times the probability of success times the probability of failure. Which also means that this inside our square root sign is also the variance. So that's kind of nifty if we need the variance for any reason, like maybe we might be combining random variables. Right? There's that possibility. Note. These formulas will only work for binomial distributions. They cannot be used for other distributions. Right, the previous way of calculating mean and standard deviation for random variables will work for any random variable. This is a shortcut if I know that that random variable is a binomial random variable. It will not work on other types of random variables. Okay. And we could do this calculation to verify the results on the previous page, but we're not going to do that right now. Is there anything I can clarify about this right now? Yes. Trinity, do you have a question, or do you need time to write it down?
Yes, I have a question. So okay. The N is the number of trials, and then P is probability?
Probability of success.
Of success. Okay, can you re-explain the standard deviation? Like, tell me what the variables mean again?
Yeah. So, let me get my little pen. All right. So for both of these, N and P are the same value, right? N will be the number of trials. Right, and P is that probability of success. Right, down here for standard deviation, it's the same. We're still using N representing the number of trials. Both of, oh, come on. I don't know why I did that. Making my lines all crazy. All right, both of the P's here are the same P. It's the probability of success. Right? If we subtract this P from 1, we get the probability in the parentheses, we get the probability of failure. Let's consider another example. All right, we have Mr. Billard's 21 AP Stats students did the activity on page 340. This is an activity about being able to determine the difference between tap water and bottled water. If we assume the students in his class cannot tell tap water from bottled water, then each has a 1 in 3 chance of correctly identifying the different type of water by guessing. Right, let X equal the number of students who correctly identify the cup containing the different type of water. All right, so we're going to find the mean and standard deviation of X. Since X is a binomial random variable with parameters N equals 21, so there's 21 trials, 21 students, each student is a trial, and P equals 1 out of 3, we can use the formulas for the mean and standard deviation of a binomial random variable. So we have a mean of N times P, which is 21, number of trials, times 1/3, probability of success, and we get 7. Which means in context, we'd expect about 1/3 of the 21 students, about 7, to guess correctly. right? Just based on the probability. The standard deviation is calculated by the square root of n times p times 1 minus p, which we get 21 times 1/3 times 2/3. Right? Again, if things are going well and you're doing your calculations properly, this plus this should equal 1. It's success or failure. Between the two of them, we have 100% of the possible outcomes. Right? So this times 1/3 times 2/3 equals 2.16, right, with the square root, which means if the activity were repeated many times with groups of 21 students who were just guessing, the number of correct identifications would differ from 7 by an average of 2.16. So again, we're explaining our result based on the given context about guessing the correct type of water. Right.
I changed my mind. You can move on.
Okay. So then we have binomial distributions in statistical sampling. All right, the binomial distributions are important in statistics when we wish to make inferences about the proportion P of successes in a population. Problem is, almost all real-world sampling, such as taking a simple random sample from a population of interest, is done without replacement. And if we do sampling without replacement, that violates independence. However, I said it in my own words, sampling without replacement leads to a violation of the independence condition. That's a problem. When the population is much larger than the sample, a count of successes in an SRS of size n has approximately the binomial distribution with n equal to the sample size and p equal to the proportion of success in the population. All right. This means that if the overall population we're sampling from is big enough, then we can say, well, our sample size is such that we can still use a binomial distribution, even though technically it's violating independence when we're checking bins, right? Because of the 10% condition. When taking an SRS of size n from a population of size capital N, we can use a binomial distribution to model the count of successes in the sample as long as little n is less than or equal to 1/10 of big N, meaning that the sample size is less than or equal to 10% of the entire population we're sampling from. If that condition is true, then I can use a binomial distribution to approximate the probabilities. Right? So when we're checking bins and we're told, hey, we're doing in a simple random sample, right? If I can justify that the simple random sample from the population is less than 10% of that population I'm sampling from, then I can still say that bins has been satisfied and I can use a binomial distribution, which is nice because mean and standard deviation are a little easier to calculate. We have a slightly easier calculation for probabilities. That's a good thing. Normal approximations for binomial distributions. Right, we can use a normal approximation for a binomial distribution if some conditions are met. As n gets larger, something interesting happens to the shape of a binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. What do we notice? Here's our first one. We see n is 10. Right, so my sample is 10. I've got probability of 8.8. Now I've got a larger sample, right, of 20. Still the same probability, 0.8. We can see that this is kind of like normalizing almost. We get an even larger n, and this really just looks like a normal curve. Or we can say it's approximately normal. So as n gets larger, right, the binomial distribution tends to look more normal. So that's kind of a nice thing too, because then we get all the tools we use with normal approximations available to us. Right, so we get this, the normal approximation for binomial distributions, the large counts condition. So this is another condition to check for. Right? If we're in a binomial distribution, right? So we suppose that X has a binomial distribution with n trials and success probability P. When n is large, the distribution of X is approximately normal with mean and standard deviation calculated the same way we just said for a binomial distribution, np and square root of np times 1 minus p. As a rule of thumb, we will use the normal approximation when n is so large that np is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Both things need to be true. That is, the expected number of successes and failures are both at least 10. If this is satisfied, we can use a normal approximation, right? Which means we get to use the normal curve, right? The area under the curve to determine probabilities, table A, right? We have a system of things in place that we can use. This is the large counts condition. Right? Again, unfortunately, I don't have an example of this in these slides. However, if you'd like to see an example, I have some in the worked examples. Or you can just ask and I can do an example after we're done. Can you raise your hand if you need a moment to write this down? So now we get into geometric settings. In a binomial setting, the number of trials n is fixed, and the binomial random variable x counts the number of successes in a fixed number of trials. In other situations, the goal is to repeat chance behavior until a success occurs. Right? These situations are called geometric settings. Right? So instead of doing a fixed number of things and counting how many successes I have, I'm going to count how long it takes for me to have a success. That's the difference between binomial and geometric. A geometric setting arises when we perform independent trials, so we still need independence, of the same chance process and record the number of trials it takes to get one success. On each trial, the probability P of success must be the same. So a lot of the things from binomials still need to be there, right? It needs to be independent, probability of success needs to be the same, right? And we're still thinking about success. However, we're changing to be, okay, well, I don't know how many trials it's going to be, but I will stop when I get one success, right? And that'll be the count. See, we need a moment to write anything down from this slide. So in a geometric set, oops, sorry. Did Jamie go back?
It's okay.
Okay, sorry. In a geometric setting, if we define the random variable y to be the number of trials needed to get the first success, then y is called a geometric random variable. Probability distribution of y is called a geometric distribution. Right? So then we get this definition here. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. Probability distribution of y is a geometric distribution with parameter p, the probability of a success on any trial. The possible values of y are 1, 2, 3, and up to infinity. Right? There's no like known endpoint until we find the success. Right? Like binomial random variables, it is important to be able to distinguish situations in which the geometric distribution does and doesn't apply. Mainly, right, are you being asked to find how long do you expect it to take to get the first success? Right, that's geometric. It's like how many trials would it typically take to get one success in whatever you're doing? That's geometric. Right, so you're looking for those kind of cues. Right, can you please raise your hand if you need a moment to write this down? All right, bye, Roel. Have a good day. All right. So here's our example for geometric probability here. We're going to consider the lucky day game. Right? And the context of this game is that a teacher normally gives his class 10 homework problems. As an alternative, he gives them the opportunity to play the lucky day game. The way this works is that a student will be selected at random from the class and asked to pick a day of the week, Monday through Sunday, so there's 7 choices. Then the teacher will use technology to randomly choose a day of the week as the lucky day. If the student picks the correct day, the class will have only 1 homework problem. If the student picks wrong, the teacher will select another random student who will then choose another day of the week, and the teacher will then randomly choose another lucky day. If the guess is correct, then the class will have 2 homework problems. The game continues until a student correctly guesses the lucky day. Right, so again, we're looking for the first success. Your teacher will assign a number of homework problems that is equal to the total number of guesses made by members of the class. Right, so that's our context for this lucky day game. Right, the random variable of interest in this game is y, which is equal to the number of guesses it takes to correctly match the lucky day game. What's the probability of the first student guesses correctly, second, third? What's the probability the kth student guesses correctly? So for the first student get the correct answer, there's a 1 in 7 chance, right? There's 7 days to choose from. They have a 1 in 7 chance of picking the correct one. For the second student to get it correct, meaning they have the first success, that means the first student got it wrong, 6 out of 7 chances, and the second one got it right, 1 out of 7. So we just multiply those, and we get 0.1224. Essentially, this is a AND situation. First is wrong and second is correct. So we multiply those probabilities as their independent events. Probability of the third student being the first correct guess is the probability of the first being wrong and the second being wrong and the third being correct. So we multiply our probabilities, we get 0.1050. The pattern is emerging that we will always end with multiplying by a success. Every previous multiplication is a failure, which yields the geometric probability formula. If y has the geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, on and on and on through infinity. If k is any one of these values, then the probability of y equaling k is equal to 1 minus the probability of success to the k minus 1 power times the probability of success. Okay, so this is a slightly smaller calculation, which is kind of nice. And again, there's ways to make your calculator do this, which is nice too. Can you please raise your hand if you need a moment to write this down? We're almost done, guys. Hang in there. So the mean of a geometric random variable, the table below shows part of the probability distribution of y. We can't show the entire distribution because the number of trials it takes to get the first success could be an incredibly large number. Right? It would be really bad luck, but it could get to 50 guesses. That would suck for the class. Right? But we see our distribution, right? We're not able to do the whole table. We can't do the whole histogram technically, but it gives us a really good idea of what it looks like. Right, the heavily right-skewed shape is characteristic of any geometric distribution. That's because the most likely value is 1. The center, right? The mean of y is 7. We'd expect it to take 7 guesses to get our first success. Right, you have a 1 in 7 chance of guessing correctly. Chances are you'll get a correct guess by the 7th guess. The standard deviation of y is 6.48. We won't get into how to calculate this right now. If the class played the lucky day game many times, the number of homework problems the students receive would differ from 7 by an average of 6.48. Pretty big swing. To calculate the mean or expected value of a geometric random variable is one of the shortest calculations we have. All right, if y is a geometric random variable with probability p of success on each trial, then its mean or expected value is 1 divided by the probability of success. All right, it's just that simple. 1 divided by p. right? Because we have a 1 in 7 chance of being successful, 1 divided by 1 over 7 is 7. Is there anything I can clarify for this slide? All right. And can you raise your hand if you need a moment to write anything down? And lastly, just like the binomial probabilities can be calculated on your calculator, we can follow the same steps to find our geometric PDF and geometric CDF. They follow the same rules. Geometric PDF is having a probability of X equaling a certain number of guesses or a certain number of trials before the first success. Geomet CDF is P of X being less than or equal to a certain number of trials. Right? And it takes the arguments of n, or not n, of probability, look at it, and the number of trials you're curious about, right? Or the K value, right? I'm going to show you guys that is there. All right, so then we've come to the end, right? We did all these fun things. We looked at all these examples, and now we've reached the end of chapter 6. That is section 6.3. All right. Now that being said, this is the only day that I get to see you guys this week, so we do not have a day of like practice problems like we have for the previous 2 sections. We will be moving on to chapter 7 next week on Tuesday. I will have a Desmos activity for section 6.3 that will be just an opportunity to practice. It will not be required and it will not count towards participation or anything like that. I do encourage you to try the practice problems in 6.3 of the chapter 6 module. See if you can make sense of them, see if you can get the answers, see if you have any questions for me, anything I can explain better. All right. Also, you should now start working on the chapter 6 assessments and see if you have any questions about those, because again, I'd be happy to support and help you guys make sure that you're doing the best job you can on those assessments. All right. Other than that, that's everything for today. I know it's been a long class. I do apologize. We had to get through this. If there's anything else I can help you with, please let me know. You are welcome to stick around and ask right now, or you can send me an email or a message somehow, and I will get back to you. Other than that, have a lovely day, have a lovely week, have a great weekend, and I'll see you on Tuesday next week.